Welcome. In this session, we'll explore using proofs that involve contradiction in a more complicated theorem. Let's suppose that we are given the sequent, which is, if it is not the case that P implies Q, we can conclude that P is true and Q is false. We begin by writing this as our premise, which is P does not imply Q. So that'll be our premise. And the next thing we do, we're anticipating that this may be a rather lengthy proof, so let's leave ourselves lots and lots of space here. And our conclusion is that P and not Q follows. Before we begin, let's do a little bit of ordinary logical reasoning. If we're saying P does not imply Q, when could that be true? Well, we know that if P is false, that it materially implies anything. We know that if Q is true, it is materially implied by anything. So the only situation in which this can't happen is when P is true and Q is false, which is the conclusion of our argument. So having satisfied ourselves that this might actually be possible to prove, let's take a look at it. If we look at the premise and we look at its structure, what we see is that its structure is a negation of a compound formula. And we don't have any rules that can immediately help us there. We then try to apply some backward reasoning, and we see that this conclusion line is a conjunction of a simple symbol and the negation of a symbol. Well, if it's a conjunction, then we know that conjunction introduction could be used. And that would entail that we have to prove P and that we have to prove not Q. Let's take the not Q part first. So what we know is that eventually what we want to do is we want to use conjunction introduction. And the previous line of this will have to be not Q. If we now have this as our goal and this as the only line that we've proved so far, it's not immediately apparent what we can do. However, if we refer to these rules, we see, well, perhaps we could try negation introduction, which is one of our forms of proof using contradiction. So let's try that. Let's set up an assumption box. And within that assumption box, we'll follow our usual method, which is we first draw the assumption box, then we draw the reason for it, which is negation introduction. We then fill in the top line, and the top line is the unnegated formula. So in this case, it is Q, and the reason for that being present is it's an assumption. And we fill in the bottom line of the box, which is the bottom symbol, which indicates that we're aiming at trying to show a contradiction. Now, what could we do? So my usual next step is I take the assumption of the box and I take everything that precedes it and is within scope, and I say, what could I do? Well, from Q, I can't do anything directly, but my goal, so some forward reasoning doesn't seem to be useful yet. However, my goal is still a contradiction or a bottom. And there are only two ways that I could arrive at that. I could either write not Q, which doesn't seem so useful, does it? Because not Q is what we're trying to prove outside the box. So that's probably not a good thing to do. The only other thing I could do is I could write the unnegated form of the premise. So if I could show that P implies Q within this assumption box, not in general, just within this assumption box, if I could show that, then I could arrive at my contradiction. And what I'll do is I'll actually say that I'm going to get there by a contradiction, which is negation elimination. Now I'm getting somewhere perhaps useful, because now I have P implies Q. Well, the structure of this is an implication, and I could use an implication introduction, which is another assumption box. Am I allowed to use boxes within boxes? Definitely, and sometimes it's our only method. So I will do that. I will open up an assumption box. I will write the reason for the box, which is implication introduction. I will write the top of the box, which is the antecedent of what I'm trying to prove, and I will write the consequent of the box at the bottom. Oh, I will write the reason, which is this is an assumption. And I will then write the consequent at the bottom. I then take a look at what I have. And I always look first at my assumption, and then Q is within scope. Oh, well, if Q is within scope and Q is what I want, then I have shown that assuming P, Q follows, and that means that P implies Q. So this is a copy. And I can't put the line down yet because I'm still using backward reasoning. But now what I've done is saying, well, from this assumption, from this premise, I can conclude that Q is false. That is, if P does not imply Q, one of the requirements for that is that Q has to be a false symbol. Well, that has given me half of this goal of the conjunction. The other half of the goal was that I need the left conjunct, which is P. And again, the question arises, what could I possibly do to arrive at that? So I look at this goal, and I look at the only premise I have, and I don't see anything immediate. However, this does follow the general pattern of proof by contradiction. So I'll try using proof by contradiction. So the reason for doing this is proof by contradiction, and I open up a box, and I fill in the top line of the box, which is the negation of the goal, so that is not P, and the reason for it being present is it's an assumption. And now, because I've run up against the premise, I can actually begin the process of numbering the lines in my proof. And then I write the bottom line of the box, which in the lowest line of the box, which in this case is the bottom symbol. And now I apply the same kind of reasoning that I applied here. In order to get a contradiction, I either have to assert P or I have to assert P implies Q. Well, I think I'll use the same kind of reasoning here, and that is I will assert P implies Q. And this has the structure of an implication, so an implication introduction is the only rule that I can see that I could possibly use. So I will produce another nested box, And the reason for arriving at this line is implication introduction. I write the antecedent as the top, which is P, and I write now I can fill in the line number, and I write the reason for it being present, which is it's an assumption. And I then write the bottom line, the lowest line of the box, which is Q, and I examine what I have. Well, what I see here is I see that P is an assumption, and then within scope, in a larger assumption box, I've assumed not P. And I know that whenever I see a formula on a line and I see the negation of the formula on another line that's within scope, I can write the bottom symbol. And so I can write the bottom symbol, and that is by negation elimination, because I'm eliminating this. That is line 4 of my proof. Now I can conclude that that is line 5, and the reason that I've done is the same, is that is, so now this is my contradiction. So this is line 6, and line 6 follows from the reasoning of lines 3 through 5. Line 7 is a contradiction, and that comes from line 6, line 1, and that is negation elimination. This is now line 8, proof by contradiction, and I arrive at that by the reasoning of lines 2 through 7. This is now line 9, which is an assumption. This is line 10, which is an assumption. This is line 11. And 11, now I can say that's a copy of line 9. I knew previously that it had to be a copy. I just didn't, at the time that I was doing it, I didn't know what the number was. And that's because I'm using backward reasoning quite persistently here. This is now line 12, and I can say that line 12 came from the reasoning of lines 10 through 11. I can now say that this is line 13, and line 13 comes from line 12. I can now say that, line 12 and line 1. I can now say that this came from negation introduction, and that was the reasoning of lines 9 through 13. And that is line 14 of my proof, and line 15 of my proof comes from line 8 and line 14, and I reasoned backwards that this was conjunction introduction. And so I have a proof of, I have a moderately complicated proof, slightly long, and it involved nested assumption boxes twice, which is the first time in these sessions that we've seen this complexity of a proof. But then we've also not seen this complexity of a sequent yet. So in subsequent sessions, we're going to add another few rules, and we'll then have the full power of natural deduction for propositional logic. Me again. I forgot to label this as bottom elimination, which came from line 4.